Your handout that you were to print for today on the mandatory preparation stuff. Let's take the same kind of day. Again, the temperature at the surface is 20 degrees. Don't get hung up on the number 20. I just made it 20 degrees. But let's say we measured with a weather balloon or something and we found that 1 kilometer up, the air temperature of the environment was 15 degrees. So, our environmental lapse rate is 20 minus 15, or 5 degrees Celsius per kilometer. Now, what we need to do is we need to try to lift air from the surface where the temperature is apparently 20 degrees and find out if it'll rise on its own or not. I don't know in advance whether we're talking this air is saturated or not. So we use the dry adiabatic lapse rate or the moist adiabatic lapse rate. So what the hell, let's try both. If we had air at the surface at 20 degrees and we lifted dry adiabatically, the temperature at 1 kilometer up will be 20 degrees minus 10 degrees, or 10 degrees Celsius. Which means our air parcel, when we lift it 1 kilometer up, has a temperature of 10 degrees, which is obviously less than the temperature of the air around it. The environment has a temperature of 15 degrees. This air is colder than the environment. If we quit pushing it, it's colder and more dense than the air around it, it'll sink. It'll just sink back down to the surface. What if this air was lifted? What if this air was saturated and we were lifting it moist adiabatically? Well, it has a temperature of 20 degrees. We lift it at a moist adiabatic lapse rate of 6 degrees Celsius per kilometer. Therefore, the temperature 1 kilometer up for our air parcel is 20 minus 6 is 14. 14 degrees is less than, which is the temperature of our air parcel, is less than 15 degrees, which is the temperature of the air around the air parcel. This air is colder than the air around it. Not much, but a little bit. By the ideal gas law, we know that that means this air is a little more dense than the air around it, which means that if we quit pushing it, it will sink. In this problem, it did not matter whether the air parcel was saturated or unsaturated. The humidity of the air parcel had nothing to do with it. Whether we used the dry adiabatic lapse rate or the moist adiabatic lapse rate, we ended up with an air parcel that was going to sink. Once we lifted it a little bit, it was colder than the environment. As soon as we quit pushing it, our cold front quit lifting it, our mountain, it was just going over a little hill. Whatever reason that we gave it, that we pushed it a little bit, it just sank back down where it came from. We call this situation absolutely stable. When the atmosphere is absolutely stable, you can forget about thunderstorms. Because no matter how you lift the air parcels, they're going to be colder than the air around them. Once you quit lifting them, they are not going to rise on their own. And the environment will be absolutely stable whenever the environmental lapse rate is less than the moist adiabatic lapse rate. Because it's our second inequality. If the environmental lapse rate is less than the moist adiabatic lapse rate, the atmosphere is absolutely stable. So in this case, we've used those numbers up at the top of the spreadsheet of the handout. 20 degrees and 15 degrees, like this was something we measured with our weather balloon. And from that, we found out that the environmental lapse rate was 5 degrees Celsius per kilometer. And a meteorologist would now immediately say, no chance of thunderstorms. How are you going to get them to rise? By the way, notice that the temperature of the environment was decreasing with height. At the surface, it was 20. At 1 kilometer up, it was 15. What if the temperature had been warmer aloft than at the surface? Remember how the signs work on the environmental lapse rate? We learned this back in the first unit. If the temperature actually is getting warmer with respect to height, like in the stratosphere, where temperatures increase with respect to height, the environmental lapse rate is actually negative. If the environmental lapse rate is negative, we have a special word for that kind of layer of the atmosphere. Does anybody remember it? It started with an I. It was an inversion. An inversion. An inversion is a layer where temperature increases with height. Now, the stratosphere is an inversion. When we have an inversion, the environmental lapse rate is less than 0. The moist adiabatic lapse rate is 6. So if we have an inversion, we are always absolutely stable. You can't really get rising motion in an inversion. You see that now? So if in an inversion where the environmental lapse rate is less than 0, that will always be less than 6. Right? So an inversion is absolutely stable. That's part of the reason why, remember we've been treating the stratosphere like a ceiling to the atmosphere? We've said that things like the things that happen down here near the surface, the troposphere, like thunderstorms and so on, they can't go up into the stratosphere. It's because you can't get rising motions in the stratosphere. The stratosphere is absolutely stable. You can't get up in, air particles from the surface can't rise up into it, so the environment, so the stratosphere is like a ceiling. It's like the top of the atmosphere. Let me do a third example here to illustrate the third possibility for stability. Again, this one's also in those handouts that you have. If your environmental lapse rate worked out to be 8 degrees Celsius per kilometer. In this case, then, we had a temperature at the surface of 20 again. Don't get hung up on the 20. That's just a number. Your numbers in your homework problems will be different. And on that first kilometer, 1 kilometer up, the temperature was 12. You now have an environmental lapse rate of 20 minus 12 is 8. Let's do the problem again where we take air from the surface and we lift it. We lift it, I don't know in advance, dry adiabatically or moist adiabatically, so let's try both. If we lift the air dry adiabatically, its temperature is 20. We decrease it by 10 degrees Celsius per kilometer, so 1 kilometer up, our air particle has a temperature of 10 degrees. Our air particle at 1 kilometer then is 10 degrees. Our air particle, our environment around it is 12 degrees. This air is colder than the environment and it will sink. If we lift that air particle 1 kilometer, it's now colder than the air around it, it will sink. But what happens if we lift the air particle moist adiabatically? Let's say this air particle is saturated and we have to use the moist adiabatic lapse rate. 20 degrees minus the moist adiabatic lapse rate, 40 minus 6 is 14. 14 degrees, which is the temperature of our air particle at 1 kilometer, is more than 12 degrees, which is the temperature of the air around it. This air particle is warmer than the air around it. Why is it warmer? Because when we use the moist adiabatic lapse rate, we got some latent heat back, right? Remember, as we lifted that air particle moist adiabatically, there was condensation going on, which was releasing latent heat. Now that air particle is warmer than the environment, he would rise. If he's not saturated, he'll be colder than the environment and he'll sink. If he's saturated, he'll be warmer than the environment and he'll rise. This is a funny situation called conditionally unstable. The condition of conditionally unstable has to do with whether or not the air particle is saturated. If the air particle is unsaturated, you're going to be cooling at a whopping 10 degrees Celsius per kilometer. You're just cooling too fast. The air will always be colder than the air around it, and it will sink. If you are saturated, you'll only be cooling at 6 degrees Celsius per kilometer. You might be warmer than the air around you, and you might actually rise. And the atmosphere is going to be conditionally unstable whenever the environmental lapse rate is between the dry adiabatic lapse rate and the moist adiabatic lapse rate. This pen is worthless, sorry. So we have these 3 rules, these 3 inequalities. You can compute the environmental lapse rate for any layer of the atmosphere. And on the homework, you'll be doing that. You actually are given temperatures at like 1, 2, 3, 4 kilometers. And from that, you find out what the lapse rate is for like 0 to 1 kilometers and 1 to 2 kilometers and 2 to 3 kilometers. And then based on that, you can determine whether the atmosphere is stable, absolutely unstable, or conditionally unstable. Most of the time in our atmosphere, the answer is conditionally unstable. Most of the time, sometimes it's absolutely stable, but like for example on Monday when we had all those thunderstorms, we were conditionally unstable. The atmosphere was it was conditionally unstable. The air was sufficiently moist that once that cold front came through and started a little rising motion, the air was rising moist adiabatically. It was warmer than the air around it, and it continued to rise all the way to the top of the tropopause. These rules about absolutely stable, absolutely unstable, and conditionally unstable, I can 100% guarantee you are on the test. You absolutely need to be able to use temperatures at 2 heights in the atmosphere to determine an environmental lapse rate, and from that information you need to be able to determine whether the atmosphere is absolutely stable, absolutely unstable, or conditionally unstable, and from that information you need to decide what that means. Let's try this situation of conditioning unstable